Today we're looking at Module 4, Lesson 22 and 23. And Lesson 22 focuses on constant rates revisited. So we want to make sure that students know that any constant rate problem can be described by a linear equation. And that's in two variables, where my slope is equal to constant rate. So we're going to look at an example problem where this really gets clarified. But we also want to make sure that students can compare proportional relationships in graphs, in equations, and in tables. So we're going to look at example 3 from your Eureka text and kind of work through this and see how constant rate problems lend themselves to be linear functions. So let's suppose Erica walked y miles in x hours. Then her average speed is y over x, miles per hour. If she walked 3 miles per hour, we would say y over x is equal to 3. So let's solve for y to get a linear equation. So y over x equals 3, multiply both sides by x equals y equals 3x. So now I have a linear equation. The only thing that is not in this equation is a b value, my y-intercept, and that's probably because it equals 0. So if x is 0, y is 0. If x is 1, y is 3. If x is 2, y is 6. If x is 3, y is 9. And I'm just solving for y when I'm choosing a random x value, just like we would when we were solving any linear equation. And then I'm going to look at a quick graph, because what I want to determine is that my slope is the same as my constant rate. So if I have these coordinate points, 0, 0, 1, 3, 2, 6, I can really clearly see, using any 2 points, that my slope is going to be 3, which is the same as my constant rate. So what that tells us is that constant rate, any constant rate scenario, can be written as a linear equation. That's all for Lesson 22. Moving on to Module 4, Lesson 23, we're going to focus on the defining equation of a line. So what does that mean exactly? We're going to be looking at how equations can look different but actually graph the same line. So students know that true two equations in the form ax plus by equals c and the form a prime x plus b prime x equals c prime are going to graph the same line when a prime over a equals b prime over b equals c prime over c. So what that tells us is that the coefficients of our equation are proportional to one another. So that means I use the same scale factor to adjust those coefficients throughout, and I'll end up with the same line. So let's check and figure out if we can make this work. Let's write three equations whose graph is the same as the equation 3x plus 2y equals 7. So I'm going to draw my graph first so that we can see whether it's the same or different. When I have my original equation, 3x plus 2y equals 7, if x was 0, then y would have to be 3.5. If x is 1, y would have to be 2. And if x is 2, y would have to be 1/2. So I'm graphing that line just by substituting those values into my equation and solving. Now let's change that equation with a constant. So 3x plus 2y equals 7. I'm going to multiply that whole equation by 2, scale factor of 2. So 3x times 2 is 6x, 2y times 2 is 4y, 7 times 2 is 14. And now I'm going to look again and say, okay, if x was 0, what's my y? If x was 1, if x was 2. And I'm getting the same coordinates as I did in my original equation. Just because I multiplied by a scale factor of 2 doesn't mean that I've actually changed my equation at all. I can do this multiple times. Instead of a scale factor of 2, let's use a scale factor of 3. Or I could divide by 2, or use a scale factor of 1/2. So I'm manipulating those equations. I can check my coordinate points, but because I scale the equation proportionally, all of these equations are going to produce the exact same graph.